Good morning, everyone. Well, I hope that the spring break week was good for you, at least maybe in terms of maybe some rest and just maybe to catch up on some things that can't be accomplished when you're busy in the semester. I think this past spring break was one of the nicest weather-wise since I've lived in Texas. I've noticed that all the spring breaks were always very wet and rainy and somewhat dreary, and we had a beautiful week. So the good thing for me is that I was able to do some things that I needed to get accomplished uh, in my academics in San Jac and also with music and things. So it's always good to have that refreshing time. And we, like I say, we were blessed with nice weather. Now, of course, we're back to the grind to finish out our class. Now, remember, if you've checked your schedule, next week we will have our third test. And it, of course, will be the same time set up, the same testing window as before. Um, Again, I think the fact that we try to spread the test out in a way so that the material is not huge is at least something that should lower your anxiety. But of course, even attempts to do that, there's plenty of material to be studied. So of course, by the end of the week, I will make an announcement about that. And of course, anything that we cover this week will be material that can be included on the test, and anything, of course, that we do next week will, of course, not be included. And then as I've been doing in the past on the Wednesday, I'll do some review problems. So basically, we will finish up the integration that we had as far as the topics for the test, and then we'll have some of the new topics that we'll be talking about today. I want to stress the fact that what we start talking about today is really something you already know about, sequences. And so without any more complication from Professor Ron, let's get started. So I'll share my screen. Now, when I say you actually already know about sequences, it is actually quite true. A sequence is basically, when you consider the limit of a sequence, you're looking at a limit at infinity. And so here's an example, for instance, in Calculus 1. And so we get all of the theory that we had in our previous class. In Calculus 1, we studied limits at infinity. And you actually studied these in pre-calculus. So for instance, you might look at the following. You'd say you have f of x equals, say, 2x divided by x squared plus 1. So that's a nice rational function. You know how to integrate it. You know, we've done so much at this point, it's like you're starting to feel like a math major. And so we could always pass to the limit here and utilize what we know about real functions. For instance, we could say now the limit as x passes to infinity of 2x over x squared plus 1. Now, when you look at this particular example, when we study limits at infinity, we want to be able to realize what happens with the degrees, especially in a rational function. So now when you look at this, you see the degree of the numerator is 1 and the degree of the denominator is 2. And so the denominator will dominate, so to speak. And so, of course, with the degree upstairs being 1 and the degree downstairs being 2, this limit would be 0. So this is just like when we think about the horizontal asymptotes. That is, the denominator will dominate as x passes to infinity. And so all of this theory that we thought about, here's another example. Here's one of the first ones we ever did in Calculus 1 that kind of lends the idea to what we did here. If we just have x passes to infinity of 1 over x, that limit is 0, and that's easy to prove just using the basic definition of a limit at infinity. So how does this impact the sequence? Well, the sequence is basically just a restriction of this. And normally in calculus, what we would do is that we would just replace the x with a letter like an n for natural number. So if we have a convergent real function at infinity, that can pass to the sequence. So here's what we're going to do. Define a sub n, and this is the notation we usually use for a sequence, where we basically think of a sub n as the output and n as the input. So we can say 2n divided by n squared plus 1. Now, where n is a natural number. So this is the beauty of the theory that you've already learned. If you have a convergent real function as x passes to infinity, then that particular calculus passes to the sequence. You simply restrict the values to the natural numbers, but that does not change the convergence. So the nice thing here is that all the theory that we had for the real functions passes basically to the sequences. So now we would write, using this calculation, the limit as n approaches infinity of 2n over n squared plus 1 equals 0. So we're thinking, okay, does this apply to pretty much everything? And absolutely. For instance, L'Hopital's rule, lots of students say, well, do I have to change to another variable or whatever? We won't always be so formal that way, but again, all theory about limits at infinity will pass to limits of sequences. And that's just an informal way of saying that if you have this, you can simply go to here by restricting the inputs to the natural numbers. The only thing is that the reverse is not true. That we don't get. But by restricting to the natural numbers, we're still passing to infinity. We just have these gaps, but that does not change the limiting process. If we have a divergent real function as x passes to infinity, then the sequence does the same thing. So formally, how do we define a sequence? Basically, it's just a function. So for instance, here's our definition. So now we'll say the limit as n approaches infinity of a function equals L, where we'll say L, element of R, is fixed. That is, it's a constant, it has a limit. So the limit here, what does this mean? Well, we just take what we used in Calculus 1. So basically here, for epsilon positive, there exists, and we can use a natural number. We can just say some natural number n, and then you don't even really have to say it's a natural number. It works either way. Some natural number such that n greater than n, little n, that is, and of course, this can be relaxed to, this can be equal to, depending on the type of argument you're trying to fashion. But again, technically, this can be a natural number or it can be a real number. It doesn't matter. It just means that this particular natural number must be greater than that n or equal to, depending on the argument you're taking. So this has some flexibility. What this is going to mean is that when you get far enough out in the inputs, that is in the natural numbers, the limit L in this particular case will get closer and closer to the actual sequence output. So just like with the limit, this will say a sub n minus L is less than epsilon. So this is like the epsilon channel that you had in calculus 1. And you're thinking, this is just exactly what we would do with horizontal asymptotes in pre-cal and cal 1 when we would draw our particular function. For instance, if you think about this function here, this is an odd function. And I mean, it's not, and then of course with the sequences, it wouldn't be continuous. It would just have a bunch of holes in it. But for instance, we could look at this. You could apply some calculus to this, but we'll be very informal. That is, we'd have probably some relative maximum, and we'd end up doing something like this. So we'd pick up this, then we'd head up through 0, pick up this, and then head back down. So we have this nice odd function, but the idea here is that all of this calculus passes to the sequence. So as n would get really large, we would expect the outputs to get closer and closer to 0, just like the function does in calculus 1. So all of this work that we've done, I mean, you can apply, you're thinking, well, if I need to figure out if a sequence is bounded, can I use calculus? Sure. The idea is that you can apply the calculus to the real valued function and then pass that along to the sequence to get a bounded type situation set up for that sequence. Or maybe we could use algebra. Maybe we don't have to be that sophisticated. So what I'm trying to show you here is that sequences are a natural transition from the limits at infinity in calculus 1. And any limit we get with the real valued function, we can pass that along to the corresponding sequence. Okay. Now, of course, remember, it doesn't go in the reverse direction, but we're not usually very interested in that. But we can always go from the real valued function to the sequence. And what I want to focus on, again, is all these nice limit theorems work. And what's interesting is that even though they're kind of boring, let me just give you a few of them for the properties of limits, because I don't want you to think, I speak with you in my conference hours, and students often say, oh boy, limits were a long time ago, and so I don't want to assume that you remember everything. So let's go ahead and look at some of the nice properties that we have. Now, as far as the notation goes, everyone, what we usually do is use A's and B's subscripted with N's to denote sequences, because that's just standard. Any notation will work. It's just like using F's and G's for functions. So for instance, here's a nice theorem, and we'll just call this properties of limits. And all of these proofs run the same way. That we want to get some good use of these today and just get some nice practice examples. So let's just suppose, just like we did in calculus 1, isn't it nice just to go back to something you already know and it be less difficult? Well, at least for a little while. So say we have a sequence A sub n that converges. So again, L will be fixed. So in this case, fixed, L, and K in the real numbers. And also we'll fixed C in the real numbers. Okay, so we're going to have the existence of two limits, and we're just going to combine them like you did in Calculus 1, and say we have another sequence that has a limit k. So again, just remember that when you think about a sequence, think back to pre-cal, horizontal asymptotes. X passes to infinity, and then say, okay, now we're just going to deal with natural numbers. N passes to infinity. So basically 1, 2, 3, 4, 5, 6, 7, that kind of thing. You get these discrete outputs. And then you think about just connecting them all to make a nice continuous function. So you can see how the theory passes naturally. But in the other direction, we'd obviously have some issues. But like I said before, just remember that this is really something you already know. So don't make it difficult. So for the first one, let's just go ahead and write the sum and the difference, just like we had in Calculus 1. So we could have A sub n plus B sub n plus or minus in the limit and get L plus or minus K. So again, the limiting process would be linear with sums and differences. So if you had a new sequence, which was either the sum of these two sequences or the differences, you could simply just write the limit as L plus K for the sum and the limit of L minus K for the difference, just like you did in Calculus 1. Now for 2, we have the limit as n approaches infinity. Say we multiply the sequence A sub n by the fixed number C. Well, just like we did in Calculus 1, we can factor that. So this will be C times the limit of A sub n, which is L. So we get CL. And I go in my Blackboard notes, I probably have more detail than you even care to know if you're interested in that. But again, the detail is simply to remind you of what you did in Cal 1. So hopefully you did treat this at least in some detail in Cal 1. So now when you look at this, we have the same calculus motivation. That is the product sequence. That is, we take the product of A sub n and B sub n to create a new sequence, and its limit would simply be the product of the limits, just like you did in Cal 1. And then, of course, if you're interested in the quotient, so it's just like what we did in college algebra the first time you talked about algebra of functions. These are functions too. Sequences are functions. They're functions from the natural numbers into the reals. So this is a natural thing to do. So of course, with this case, we would certainly take the quotient of the limits, assuming that K was non-zero. Okay? Now, I've got this great list of special limits, but before I get to that, I just want to remind you of another limit theorem in Calculus 1 that served us very well. It's called the squeeze theorem. So let's just state that. Go back to your Cal 1 notes and look through that. Squeeze theorem. Because all of this will be documented very well there. So in this case, again, we're going to fix L, element of R, and suppose we have sequences, and we're going to have 3 in this case, A sub n, B sub n, and C sub n. Then if, here's our hypothesis, we have the limit as n passes to infinity of A sub n being the fixed number L, and also coinciding with the limit of the sequence B. And there exists, now we need an inequality, say again, an n, some natural number that we would think of in the definition of the limit of a sequence, such that eventually, that is eventually, we're going to have C sub n sandwiched or squeezed between A sub n and B sub n. So this strict inequality can always be relaxed depending on the argument you're doing. If you have one and you need to make it, equal to, then just bump it up to the next natural number. There's plenty of flexibility there. And I say that because sometimes your arguments need that equality just to make them a little bit cleaner. Then, so what you're thinking is that these two sequences converge, just like the improper integral, they converge. And then you're thinking eventually the C sub n will be squeezed between the two sequences A sub n and B sub n. So it's natural to assume now that this limit would also exist for C sub n. So then the limit as n passes to infinity of C sub n will also be L. So the idea, and this is something in calculus that and in mathematics that you will see in general. Eventually, it's true. Okay, things could be hopping all around the place before this uppercase n. It doesn't matter. N is passing to infinity. So as long as this is true, eventually, and that just means, well, for infinitely many values of n, and that's all you need. It's like a function being continuous almost everywhere. If you go to the university and you study more advanced math, Lebesgue measure, you get to that description almost everywhere, and usually almost everywhere is fine. We don't have problems integrating functions that have discontinuities as long as we can keep track of them. If they've got infinite ones, that's a difference. But if they've just got holes in them, and for instance, continuous almost everywhere, keeping away from the infinite discontinuities, we can still integrate it. So the idea is that we don't always get, the perfect situation. We just know that we have what we need eventually. And this will be a theme that's going to run through our work with sequences and series. So again, remember, as long as we get this eventually, then we have this. Now, here's one interesting theorem that is kind of new, and it's called the absolute value theorem. Absolute value theorem. And this one is often very useful in conjunction with the squeeze theorem. And we'll do some examples of these. So for instance, let's have the following. Suppose A sub n is a sequence. If the limit as n passes to infinity of the absolute value is 0. That is, if the sequence doesn't change sign positive and negative or whatever, then this is somewhat not necessary. But the idea is that if it does, and you can actually provide the existence of this limit being 0, then this says something about the original sequence. So basically, when you think about a result like this, you're thinking, well, maybe I have a limit that I know a lot about. You know, I actually know a lot about a particular limit, but then it starts to alternate sign, or I get something that you know, I think I know what this should be, but what's gonna push me across the finish line, so to speak. And here's a very simple example of this, and it's easy to use. The proof is even easier. So for instance, say we had a sequence that looked like this. Say something that alternates in sign. So we've got a sequence that's defined by -1 raised to the nth power divided by n squared, where n is a natural number. And so we can see in this particular case that if we just define this, a sub n will be -1 over n squared when n is odd. And of course, when n is even, the -1 will absorb. So this is a very simple example of what I'm talking about. N is even. Okay, so basically, the absolute value of a sub n is just the absolute value of -1 to the n divided by n squared. Now, of course, we can apply the absolute value upstairs and downstairs, and this will give us the absolute value of -1 to the n divided by the absolute value of n squared. So of course, the negative here will absorb in the absolute value for each n. So this will just be 1 over n squared. So when you think about doing this argument, we're basically fixing an n and saying, okay, positive or negative, either way, the absolute value will absorb that. And then we're seeing that the absolute value of our sequence is just the standard sequence 1 over n squared. So now, oh yeah, I've got so many examples here, too many examples. So now what we can see is we can focus on the fact that we have an understanding of this. So we know that the limit as n approaches infinity of 1 over n squared, that's the same as just 1 over n is 0. So this implies the limit as n approaches infinity of -1 to the n over n squared is also 0. So basically what this does is it allows you to focus on the sequence of absolute values. But here's the case. This limit must be 0. Otherwise, this is no good. Now, the idea is that at first, when you see this, you're thinking, oh, it's a lot of work. But when you start using it, you'll see that basically the alternation in sign, each time you're hovering very close to 0 as n gets larger and larger. And so the alternation in sign does not affect the calculus. It does not affect the limit. For instance, again, very simple result, but a very, very useful result. So don't think that, you know, when you look at these that, oh, this is so easy, I don't even have to think about it. Do, because in the long run, what we're going to see is that sometimes these very, very simple results make our work very, very seamless. Now, I've got a couple of things that I want to mention about some special limits. And I've got a list here. This is where we think that we want to apply L'Hopital's rule if necessary. So here's a list that we will use. And I'm just going to entitle this Special Limits. So when I write some of these down, you're going to look at these and say, oh, that's L'Hopital's rule. So the first one, again, is a L'Hopital's rule. The limit as n approaches infinity of the natural log of n divided by n. That's like natural log of x divided by x. This is 0, and that's a L'Hopital's rule proof. Most of these you can prove with L'Hopital. The next one, of course, you can prove with L'Hopital if you want to use the natural logarithm, like I've done before. This will be, when these come up, you can always reprove them. But if you already have the result, just like we have an integral result, you can use it and move the calculation forward. This limit is 1. And again, this can be effected using L'Hopital with the natural logarithm. So when you nth root n as n passes to infinity, the limit is 1. Just like when we did, we had an example of, like, for instance, 1 plus r over x is raised to the x power that you did in college algebra with continuous interest. It's the same thing. And another one that's very similar to number 2 is this one. So we're going to fix x positive, and we'll have the limit as n passes to infinity of x to the 1 over n is also 1. So what's interesting here, and this is a nice comparison here. Here, as you nth root n, as n passes to infinity, you get 1. And then from your experience in calculus, if you take a positive number and you just keep nth rooting it, that is 1/2 power, 1/3 power, 1/4 power, you just drive the number down. You drive the number down or up to 1. And that's a very fascinating fact right here. So again, another very interesting special sequence. 4, and here's our bread and butter. Let me give this is from your work with geometric sequences, and this is so important. So we want to fix, my favorite word, fix, it means constant. Fix x element of R where x in absolute value is less than 1. Okay, so again, x lives between -1 and 1 here. So x is in there. So the absolute value of x is strictly less than 1. Here, the strict is very important. And of course, you know what this is. The limit, very similar to this one, as n passes to infinity of x to the n. Now, just like the nth rooting drives the number to 1, the nth powers drives the number between -1 and 1 to 0. So this is what confounds so many students who live by the calculator. If you live by the calculus, then you have no problem with this. And it's really important. So we think, how do we know when things are working out? We take our intuition and we couple it with our understanding of the calculus. And that's where things start to make more sense. So again, even though isolated cases of these seem really simple, these can turn out to be very useful. Now, the one I was just talking about, again, the compound interest, so to speak, or the continuous interest, in this case, fix x, a real number, and this is just like what we had with the continuous interest. N passes to infinity, and you can use, again, the L'Hopital's rule, x over n raised to the nth power. Well, remember back in college algebra, that x was the r. the annual rate of interest. So now, and we notice when n passed to infinity, we got the PERT formula. We got e to the r, p e to the rt. So this, instead of being e to the r, will be e to the x. So again, a very useful result that you've seen in your previous course. Again, we can use L'Hopital here with the natural logarithm. And another one that we're going to use when we get to Taylor series, and again, I want to, let's say, again, fix x. I think it's important. I don't want you to think that, you know, when we look at these examples here, ladies and gentlemen, x is fixed, n is varying. Okay, that's really important. Here, x is fixed, n is varying. And that's why I'm trying to make a bigger point of this. They're not both varying. This isn't multivariable calculus. And again, you you have to be very careful that when you are doing that, that what you're writing is making sense. So fix x a real number. And here you're thinking, well, why do we care about this, Professor Ron? Well, later on when we get to L'Hopital, we're gonna start. Taylor's theorem. We're going to be looking at derivatives of polynomials, and the n factorial will kind of creep into our existence. So if we raise x to the nth power and we divide by n factorial and let n pass to infinity, well, intuition says if x is fixed, eventually the n factorial will definitely dominate and drive this particular expression to zero. And that intuitively is exactly what goes on. So the idea here is that the arguments that you use, and again, as you look in the lecture notes on Blackboard, are either an algebraic motivation or a calculus motivation based upon L'Hopital. And just like when you do your integrals, these are very convenient limits to have on a note card, just so as you see them, you're like, oh, there's my special limit, let me use it, okay? Now, what I found is as I have used different calculus books and I have taught over the years, these types of limits come up over and over. And you don't want to have to reinvent the wheel every time you see them. I have no problem with that. It's like on my last pre-cal class test, I had a problem about half-life. And the students were very wise. They said, well, you know, Professor Ron always worked this from the solution to the differential equation, but they just said, well, the book has a nice, neat formula. And so when they did their problem, they went straight to the formula and then they solved for t, you know. And so I thought, well, good for you. I said, that's fine. And the beauty of that is that they felt like, okay, we have shown this when Professor Ron does the problem, this is always the result. So we're going to use that result. So I was very happy to see that. There were other things I wasn't so happy about, but still, that was a good use of the mathematics. And when you find that you see patterns, that means you're recognizing the mathematics that's at work. So that's very good. So again, put these on a note card. This one will come back later. The rest of them, or at least this one, we will use quite a bit, number 4. Now, special limits out of the way, there's a couple of things before we get to the monotone convergence theorem. But I wanted to do just one other example before I do that, before I state monotone convergence. So here's just a very simple example of a limit that uses some very cheap algebra, so to speak. So we have a sub n is the base e raised to the nth power divided by 4 to the n. So I want to use one of the special limits that we just talked about. Now, of course, you know, you're thinking you could also work this problem, even though it would be more difficult. You could say we could change the base. We could change the base to e, and then the then maybe we would get an example that looked like, the numerator grows less quickly than the denominator. The denominator dominates, boom, we get zero kind of thing. But that's a terrific argument. But now what we can see is that if we were asked to compute the limit, we can first notice that this is just laws of exponents. And so we can say e over 4 raised to the nth power. Now, one thing we're going to notice is the following. So observe. We know that e, this very nice transcendental number, lives between 2 and 3. So when we think about that, we're like, okay, 2.7182, et cetera, like pi, never repeats, never terminates, a very, very special number. And then we're thinking, okay, well, 2 over 4, e over 4, 3 over 4. So equivalently, we see that the absolute value of e over 4 is less than 1. So now we're thinking, okay, well, this won't be a difficult limit to compute. So if we think about our special limit here, then we already know what the answer is. So we can apply 4. Just like I say, these are great to have to be able to access so you can move your calculations forward with confidence. So now this implies that the limit as n passes to infinity of a sub n will now be the limit as n passes to infinity of e sub n over 4 to the n, which is the limit as n passes to infinity of e over 4 raised to the n. So now we just invoke this particular restriction that we have computed, and so we get 0. So again, that's a special limit. The thing is that you actually studied this with geometric series. I'm going to say something about that today. This is a very important limit. As you raise a number to higher and higher powers that lives between -1, you drive it to 0. Okay, so again, when you get to the university, and maybe some of you take advanced calculus or real analysis, then you will discover a lot of these properties in a more arithmetic way. Again, the key is realizing here that everything you've developed up until this point, should start to feel intuitively obvious as well as mathematically obvious. And when we bridge the two, that's when we feel good about what we're doing. Now, you're thinking sequences? We've been studying sequences for a long time, Professor Ron, and I completely agree with you. If you've listened to anything I've said to this point, I have said nothing that's remotely challenging. Basically, I'm just picking up pieces that we've already discussed. Limits at infinity. When we talk about limits of sequences, we're just looking at limits at infinity from calculus 1. And all that calculus just passes along. Now, there's one result that is actually quite important, because as we make the transition from sequences to infinite series, we're going to need a theorem that's going to tell us about convergence. And here's this major theorem. It's called the monotone convergence theorem. Monotone convergence theorem. You're thinking we could say MCT. I don't know. That never, sometimes I just say, maybe we'll use that, since that's a lot to have to write. So and I'm going to define what monotonic is, or monotone, monotonic. I'll define that, but I'll just say, and this is interesting. A monotonic sequence, that is bounded must converge. Or you can just say bounded monotonic sequences converge. That's the quickest way to say it. You can say bounded monotonic sequences converge. What do I mean by converge? That means the limit exists. So for instance, just like when we were talking about improper integrals. So monotone convergence theorem applies to the monotonic sequence that is bounded. Okay, what's monotonic? Okay, so for instance, monotonic sequences they're in two cases, two categories. The first one is non-decreasing. Non-decreasing. So we'll just say we're using sequence A sub n. So we'll have A sub 1 is less than or equal to A sub 2, less than or equal to A sub 3, less than or equal to A sub 4, etc. Basically, when you say something is non-decreasing, the terms don't get smaller. They don't ever decrease. They may hover. They may be like 2, 2, 2, 2, then 2.1, 2.5, something like that. They uh, obviously a constant sequence would be monotonic. Not very interesting. The idea is that when we say something is non-decreasing, as we move throughout the sequence, none of these inequalities will ever be violated. So non-decreasing is really what we think about is as an increasing sequence. But things could hover for a while. 2, non-increasing. So this is just going to mean that the sequence terms don't get bigger. So we can say A sub 1 is greater than or equal to A sub 2, greater than or equal to A sub 3, greater than or equal to A sub 4, etc. So again, the sequential terms do not increase. They could hover for a while and then drop some. So this is what we think of as a decreasing sequence, but with the ability to hover around a particular set of real numbers. Say, like I say, we could have a sequence that here's an example of this one. I'll just list the terms. Say we have 5, 5, 5, 5, 5. Then we have 4, 3, 2, 2, 2, 2, 1, etc. Something like that. Non-increasing. So again, we just open the door to the fact that we can hover around a number. Like here we're hovering around 5, then we hover around 2. But in no situation do we ever have successive terms where the last term would be what? Bigger. It's non-increasing. So again, this is what you already know. It's just the terminology that we need. Now, bounded is actually quite simple. So we've got monotonic and bounded. Let's write down what that means. For instance, the sequence A sub n is bounded if and only if. Now, here's a more formal definition, but we'll usually just be glad to sandwich the sequence outputs between two real numbers that are fixed. If and only if, we'll say there exists some positive number m such that, now of course the sequence may alternate in sign or have different values. We'll say that a sub n in absolute value would always be less than or equal to m. So this is more formal in thinking that, for instance, if we had a sequence that was bounded, and we won't even probably be this formal, say we have m here and the additive inverse of m here. So these would be like a little channel. And say we have 1, 2, 3, 4, 5, 6. These are the inputs. So if we were to mark off or plot the values, say we have a value here, we have a value here, 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 maybe here. The idea is that if the sequence is bounded, then the outputs, the actual sequence will live between these two numbers. It's bounded. It doesn't pass to infinity, okay? You know, we think about the sequence n, a sub n equal n. Well, that's clearly not bounded. It can be as big as you like. It passes to infinity. What's the limit of n as n passes to infinity? Infinity, clearly. So when you think about a bounded sequence and then you add the additional non-increasing or non-decreasing, that kind of forces the convergence. So when we say must converge, basically what this is saying is that the limit as n passes to infinity of the sequence exists. So when we say a sequence converges, it's just like saying an improper integral converges or a function converges in the limiting processes that we did in Calculus 1. So again, this right now, you're like, Professor Ron, this is, it's interesting. It's like, I'll give that to you. And most students at this point, they say, well, why would we ever really be concerned with this? And my focus here is that this will become very, very important when we talk about some of the convergence tests for real infinite series. And so right now it might seem a little bit interesting, that yet not very applicable, but trust me, there'll be times when it will be very useful to us. So now what I want to do is say a little bit. I've got some examples here. I tell you, let me see, let me put this one here, move this one over here. Let's go to a couple examples. Let's look at a very simple example about boundedness, like we've done here, and monotonicity, so to speak, just so you can get a feel for this. I'll take a real simple one and you'll look at it and say, well, I already understand this, but let me give you an idea of what's going on here. So in your WebAssign, you might have a sequence that's really simple like this. So we have a sub n equals 4 minus 1 over n. And here's what we want to do. Prove a sub n is monotonic and bounded. Now, usually what students like to do, they like to look at the bounded first. They're thinking that would be the easiest to do. So first, and this can be done any way you like. There is nothing there, and if you're just asked to say, is this bounded? You figure it out and then you click yes. So it's somewhat difficult to test, but let me just show you, this is something you've already been doing rather intuitively. So now, for instance, we might say, okay, well, n, let's do bounded first since it's simple. So we're going to have n, in this particular case, is a natural number, right? So we see that n is greater than or equal to 1. Natural numbers start with 1, 2, 3, 4. And then we're thinking, okay, well, we need to reciprocate. So now if and only if, in this particular case, we would have 1 over n is less than or equal to 1. If we reciprocate this, we flip the inequality, and this is clearly bigger than 0. We're not reciprocating 0. We just know that if we have a natural number and we reciprocate it, it's still positive. And now we need a negative. So let's go ahead and multiply by a negative. So we'll have -1 less than or equal to -1 over n. And of course, the additive inverse of 0 is still 0. So again, reciprocate, multiply by a negative. So this means that we get all of these get negatives. And again, the inequalities flip around. And then we want to add 4 to all sides. So 4 minus 1 less than or equal to 4 minus 1 over n less than or 4 plus 0. I'll just write it out. So equivalently, we have 3 less than or equal to 4 minus 1 over n less than 4. Now this can be crude. It doesn't have to be formal. We just now know that if we wanted to use the m in the last definition, we could take m equal to 4, and that would work. So then we could say, in this case, a sub n in absolute value is less than or equal to 4 for n element of the natural numbers. Even though this is never negative, that would certainly be a value of m that would work. And so by definition, we say bounded. Now, this is a very simple argument, and you probably wouldn't have to think too long to say, yeah, that's clearly bounded because the 1 over n, it's not going to diverge to infinity. It's going to get smaller and smaller and converge to 0. So this is though crude, it does support the fact that this particular sequence is bounded. Now we want to say, what about monotonic? Okay, so we'll say monotonic. So we'll do the same thing that we're doing when we get to series. We'll do these types of calculations with the inequalities. Again, very simple, ladies and gentlemen, but the inequalities we build from the ground up, and that gives us what we need without having to just kind of, what's the inequality? Let's just build it. So now, for instance, we want to say that if we look at this and we think about this particular setup, how are the n's affected? So for instance, we might say n plus 1 is greater than or equal to n when n is a natural number. So again, that would be true. And then we need to reciprocate. So if and only if, we'll have 1 over n plus 1. It's kind of very similar to what we've done here, is less than or equal to 1 over n. So we're going to do the same type of calculation, but now we're focusing on the n's. If and only if, now hit with the negative. So we'll have -1 over n is less than or equal to -1 over n plus 1. And now we can add 4. So we'll have 4 minus 1 over n less than or equal to 4 minus 1 over n plus 1. But of course, this is just the definition of a sub n, and this is just the definition of a sub n plus 1. So a sub n is less than or equal to a sub n plus 1. So now we see in this particular case that the terms, they could be hovering, but they're certainly not getting smaller. So we say non-decreasing. Non-decreasing. So it's impossible for the terms to get smaller based upon our calculations. So we'll say non-decreasing, again, monotonic. And now we've got a bounded monotonic sequence, a bounded sequence that is non-decreasing. Therefore, it must converge. And you're thinking, well, I can do this limit, Professor Ron. So what I'm doing here is taking a simple example to show you about how you consider boundedness and monotonicity. and how it impacts what you already knew from Calculus 1. And so we'll say by monotone convergence theorem, A sub n converges. But you already know what the limit is. That is, we can use our limiting theorems. We have the limit as n passes to infinity of 4 minus 1 over n. And of course, we can apply the limiting process in both. This is just a constant. And of course, the limit of 1 over n is 0, so we get 4. And that's no surprise at all. But this limit as a sequence exists because of the monotone convergence theorem if we use that context. Now, of course, if we're thinking, forget monotone convergence theorem, I'll just use the calculus from calculus 1, 4 minus 1 over x and let x go to infinity. Boom, there you go. That'll work too. But what I wanted to do is recast this in terms of a sequential result that, again, the calculus will not always help us with the infinite series. We need a result that just focuses on the sequential argument, okay? So again, when you looked at this, you're thinking, I know that limit, it's 4, Professor Ryan. You don't have to do all of this. But what I want you to do is see a very simple example of how we just motivate the idea that a particular sequence or even a function like in calculus 1 is bounded and monotonic. Remember, and at first it's a little bit awkward, but when we say non-decreasing, the terms never get smaller. When we say non-increasing, the terms never get bigger. They can hover, but they never get bigger. So if you think about it that way, when you speak the word and then just do a little quick thought about what that means, it won't be so difficult. Now, when it comes to using the monotone convergence theorem with maybe a more elaborate example, we want to think about that too. But I'll hold off on that. This actually has to do with a WebAssign problem, but I want to go ahead and motivate some ideas from the series. So digest this first, and then there's a nice WebAssign problem that has a bunch of square roots in it, where you can, again, use the same type of argument thinking about induction, where things are a little bit more abstract. But I want you to digest this first. Now, so sequences, just like the limits at infinity in calculus 1, pretty much straightforward. And so what do we like to do with sequences? Well, you learned this in pre-cal. So 9.2, this will basically just be series and convergence, just the preliminaries. So again, it's almost been like we've been doing pre-calculus pretty much today, adding in the calculus that we know. I mean, what I'm saying is that all of this began in pre-cal, and then of course you filled in a lot of details in calculus 1. So for instance, what we want to do in this case is to make a certain comment here. That is, we are interested in creating a new sequence by systematically adding the terms of a given sequence. The idea now is that I want to focus on a lot of the techniques and not get mired down in so much arithmetic that you miss the boat. So again, when always go back to that background that you have from Calculus 1. It'll be very helpful. So what we can do, in this case, we'll just say let A sub n be a sequence. We're very informal, ladies and gentlemen. We just refer to a general term as the sequence, like we say, let f be a function. We're pretty lazy, but this is standard notation, and if you do that, I'll know exactly what you mean. So we're going to create a new sequence. So we're going to say S sub 1, and this is going to be an uppercase S. So we're going to create a new sequence by systematically adding the terms of a given sequence. So S sub 1 is going to be A sub 1. Now, again, you might think, who thought of this? This is crazy. Well, someone thinks of it, and then they decide when they study it that it actually turned out to be really, really amazing. And so here you have it. This just opened the door to the study of convergence, and everybody jumped on the train and, went crazy, so to speak. So now S sub 2, systematic. So A sub 1 plus A sub 2. Okay. So now we can see, okay, well, all right. So we've added these up, and we're thinking, we'll say more about that. S sub 3, which is the third term of the sequence, will be A sub 1 plus A sub 2 plus A sub 3. So basically, when we look at this and we think about what we're doing, this is really A sub 2 plus S1, and this is A sub 3 plus S2. So this is recursive, okay? And then we say S sub 4, well, we'll just add the first 4 terms of the sequence, starting with the first one. So it is systematic. I mean, it's not completely random. So A sub 1 plus A sub 2 plus A sub 3 plus A sub 4. So if we keep doing this, we're going to think, what would the general term of this new sequence look like? Well, we would just add the first n terms of the given sequence. So this would be A sub 1 plus A sub 2 plus A sub 3, and then, of course, ellipsis to the nth term. So when we think about this, ladies and gentlemen, you think back into your history and you think, oh yeah, I remember back in pre-cal, basically by the time I was so tired in the class, we just finished trigonometry and conic sections, and then my professor wanted me to understand partial sums. So this may be a little bit foggy to you. So what we're seeing here is that this is just basically creating a sequence of finite sums, a sequence of partial sums. The first sum, the second sum, the third sum, the fourth sum. And then you're thinking, okay, well, could we write this in a way that might be a little bit more convenient than having to do all of this? Sure, we can use our sigma notation, and we can just say k equals 1 to n of a sub k. Of course, we need a new index here because n has already been taken. So this just means add a sub 1 to a sub n, as we've done here. So what we basically see here is we generate a sequence S sub n of partial sums. Partial sums. So the idea is that, okay, all right, so that's a good thing, right? And I'll say affirmative, because if we create a sequence, then now, of course, like we did at the beginning of the class, all the theory from the sequences gets transferred to this thing, to this object, because it's a sequence, okay? So we're thinking, oh, okay, so as n passes to infinity, we basically generate an infinite sum. Okay, so for instance, let n pass to infinity. Then the sequence S sub n converges if and only if the limit as n approaches infinity of S sub n exists, right? If and only if this sum, which now replaces n with infinity, is finite. So if and only if the infinite sum, in this case, and now of course, we don't have to use k anymore since n is now infinity, we can use n, not to be confusing. The partial sum would have to be written this way, but now we can just say n equals 1 to infinity, since there's no confusion, a sub n is less than infinity. So what do we call that? That's what we call an infinite series. It's just an infinite sum. This is the name that drives everybody crazy in calculus. This is called the infinite series. So when we look at this, we just think, okay, partial sum, finite sum, pre-cal, okay? Finite sums always converge. So they have all kinds of nice properties, the limit properties that we enjoy. Now, again, we're thinking when it comes to these infinite sums, if they converge, then we have all those nice limit theorems, at least some of them, that will pass to this. So the key here is that when we start thinking about sequences, we have this new object called the sequence of partial sums. And then we say, okay, well, if this sequence of partial sums converges, then the object of convergence, namely the infinite series, must be less than infinity. And when I say less than infinity, basically I'm just saying that it's a fixed number. It doesn't pass to infinity or diverge to negative infinity or whatever. So the key here is that you're thinking, well, we're going to have a lot of hypotheses here to figure out how to understand these. And in some cases, the hypotheses will guide us and tell us exactly what we need to do in order to either compute the sum if it's available to us, or figure out if this is actually less than infinity. So the idea here is that we move the level of abstraction up just a little bit to develop a new sequence that we have found to be very, very useful. And then later on in this chapter, we will define the cosine and the sine in terms of these objects. That is, they will have infinite series representations. So now you see why in pre-cal we don't define the trig functions like this. We go to a more geometric approach, which actually helps us to solve problems. When we think about what we do here, we will know that whatever we generate in this case will be consistent with what we did with the unit circle. And we may find very nice uses for these objects, but we will never ever dispose of our geometric interpretation of sines and cosines, because that is tantamount to doing many, many problems which we need. Okay, so let's look at a couple of examples of this new object. So before we actually do state any theory, let's look at some examples of some partial sums that we actually, might understand. So here's an example. So in this particular case, we're thinking, what kind of situation would be available to us? For instance, are there some sums that we could figure out S sub n and then pass to the limit in a fairly simple way? Here's an example. So I'm gonna start this one working it from a very simple standpoint. So let's see here. Let's see what we have. Yeah, let me write it this way. So we have 3 and we have 2n plus 1 and 2n minus 1. Now, in this case, what we want to do is compute the sum. And you're thinking, this seems kind of a far cry from what you just talked about, Professor Ron, but not really. When you look at this mimicking this is the infinite series, and we know what a sub n is right there. So you're thinking, is this a special type of sequence? Is it going to give us a way to determine the sum here? And actually, yes, because it's a special type of in this case, sum, which I will define. So now you're thinking this 3 here, we'll just use basic properties of sums to factor the 3. So we'll say 3, doesn't matter if it converges or not, we can always factor constants because they don't have any dependence on the n. So now we can kind of focus on this as being the a sub n. And so we're thinking, how can we figure out this sum? We need to look at the sequence of partial sums. So first what we'll do is now define S sub n. And notice we start at 1. So we're going to say k equals 1 to n of 1 divided by 2k plus 1, 2k minus 1. Now, when you look at this, you're thinking, okay, we do have something at our disposal called partial fraction decomposition. That is, if we reverse the process from college algebra, what'd you do in college algebra? You had all these fractions, and you took a distinct copy of every factor in the denominators, put it together, and had an LCD. And then you solve the problem by basically erasing the denominators by multiplying through by the LCD. Now what we're doing is going backwards, which is what you do when you decompose a fraction. And it's common sense. So if you don't have all the representatives of the types of factors in the denominator, then you left something out clearly. So now what we want to do is decompose this. So let's do a little sidebar. So we'll have 1 divided by, so we don't want to do this in terms of the sum here. Let's just do a little sidebar here first. So 1 divided by 2k plus 1 times 2k minus 1. So this will just be a divided by 2k plus 1 plus b divided by 2k minus 1. This is really simple, but simple is good. Now, the LCD, of course, is what we've got here. So we'll just go ahead and run it through to remove all of the denominators. So this will give us 1 equals a times 2k minus 1. These are the easy ones because they're linear. And b times 2k plus 1. So the only way that this is going to work, ladies and gentlemen, is that this series actually telescopes, and that is an infinite number of terms actually absorb. And that's the key to this type of problem. So now we can work on this. So for instance, here, what we want to be able to do is to choose values that'll be really simple. So now let's do this. Let's say 1 equals, so we have 2a, we have k minus 1/2, just make it a little bit simpler, plus 2b k plus 1/2. That way, when you look at this, it's easy to figure things out. So factor the 2 here, and we have this. So now we'll say k equals 1/2. So if k is 1/2, that annihilates this term. So we have 1 equals 2b And so we have 1/2 plus 1/2. So that's going to be 2b times a 1. So divide by 2, b is 1/2. So now we can do k is negative 1/2. Now let's do k equals negative 1. We don't have to take derivatives or doing anything fancy here because, again, this is really simple. So we have 1 equals, so now notice this term is annihilated. And we have 2a, so we have negative 1/2 minus 1/2. So that'll be a 2a times the negative 1. So now we can divide by negative 2 if and only if a equals negative 1/2. And now you're thinking, oh, I see it, equal and opposite, equal and opposite. Now what we can do is we can go back to our partial sum and rewrite it. So this implies that the partial sum S sub n, which is k equals 1 to n of 1 over 2k plus 1 times 2k minus 1, can now be written. Now here's another thing. We've got this partial sum, and then the other sum, we'll remember this 3 up here and do all of that. So we're going to figure this part out and then multiply the final result by 3. So don't think we've forgotten this. I'm just focusing on the more challenging part. So now this equals k equals 1 to n. And so now we have the a. So we have what? Negative 1/2 2k plus 1 plus 1/2 right here, 1/2 2k minus 1. And so now, if you like, we can just go ahead and factor the 1/2 out of both of these. So this will give us 1/2 k equals 1 to n. And so this gives us 1 2k minus 1 minus 1 2k plus 1. So what we're saying here is that now we've written the partial sum in a way that's going to allow us to easily analyze it. So now let's do the limiting process. So I'm breaking this down into several steps so you get all the steps. So now let's continue. So now we can go back and write this. And this is the most important part right here. Right here. This is S sub n. At least how we've defined it right here. So now we'll say that our infinite series n equals 1 to infinity, in this case of 3, divided by 2n plus 1 times 2n minus 1 will now be, so now we'll go back and we'll pick up the 3. So we got 3 times 1/2. And notice what's interesting about this in this particular case is that we can start to unravel this in a way. So we can just write down the particular values that we need here. So let's go ahead and unravel it. So this will be the limit as n approaches infinity. And so let's go ahead and start doing it. And now we take the replacement here. Notice we have the 3 that we factored, we have the 1/2, and now we look at this. K equals 1 to n, 1 divided by 2k minus 1 minus 1 divided by 2k plus 1. So of course, 3 times 1/2 is 3/2. So we have the limit as n approaches infinity. Now we can start to break it down a little bit. So let's just write down several terms and see that this telescopes. So now we'll have k equals 1. So for k equal 1 here, let's just write it down. We have 1 over 2 minus 1 minus 1 over 2 plus 1. K equal 2. Now we have 1. Again, we have 4 minus 1 minus, now we have 4 plus 1. K equals 3. We have 1. Now we have 3, so we have 6 minus 1 minus, now we have in this case 6 plus 1. I'll write down several so you'll see the pattern. Now we have k equals 4. So we have what? 4 times 2, so that'll be 8 minus 1 minus, now we have 8 plus 1. Now we keep going. I'll just put in as we get closer and closer to n. So we'll have k equals, say, n minus 1. So we have 1. So we have 2 times n minus 1 minus 1 minus 1 over 2 times n minus 1 plus 1. And then the very last one, k equals n. So we have 1 over 2n minus 1 minus 1 divided by 2n plus 1. Let me move the cursor back over here. There we go. 2n plus 1. Again, replacement there, close brackets. So now this gives us 3/2, the limit. Now we can see that the sum actually telescopes. So now we've got what? 1. Here we have 1/3. Here we have 1/3. Here we have 1/5 with a minus. Here we have 1/5. Here we have 1/7. Here we have 1/7. Here we have 1/9. And I have to do an ellipsis. And here, notice we have 2n. Let me just do a little sidebar here. So we have 2n minus 2 minus 1, which is 2n minus 3. And here we have 2n minus 2 plus 1, which is 2n minus 1. So these are our little sidebars here that we can do our side calculation and add here. So this will be 1 over 2n minus 3 minus 1 over 2n minus 1. And then the very last one, 1 over 2n minus 1 minus 1 over 2n plus 1. Now, the thing about these telescoping sums is that the first time you do it, you need to write out a few terms just so you can see. You can note here, ladies and gentlemen, you're thinking, okay, these are going to start to absorb because they basically catch up to each other with different values of k. And so you get an output and then it's additive inverse. So now if you look at this, notice absorb, absorb, absorb. Now that's going to absorb with the term that we didn't write down here. This will absorb, absorb. Now the only thing that's not going to absorb is the 2n plus 1 because that's not in any of the previous terms by construction. So you're thinking, this is so easy. Now, the thing is, and a lot of students will say, this telescopes, I'm just going to figure out the first few terms and then forget about the tail end of it because it's just going to go to 0. Well, the first time you do it, you need to write out some terms and basically convince yourself that we definitely have a telescoping sum. So now when this construction occurs, that is when you have infinitely, basically infinitely many terms absorbing. This is what we call telescope, telescoping, telescoping sum. All these terms are kind of interesting. Telescope. We say the sum telescopes when we have all of these terms absorbing. Okay. And then the idea is that, oh, I see what you're saying. When we analyze the partial sum, so notice what we did. We factored the 3 initially just to get it out of the way, and we analyzed the partial sum by partial fraction decomposition. And then we move back to the original problem, which basically said this. The original problem is just 3 times 1/2, right here, right there, where the limit here is n passes to infinity of the partial sum. And then as we break it down, we're seeing that as we generate the terms using the differing values of k, that we get a very, very simple partial sum. Our partial sum is easy. And here's the case. We don't always have this luxury. Most cases, we can't get this much output. We're lucky if we can figure out whether or not the series converges or diverges and be happy to have it and then approximate the sum when it converges. But notice here, what survives? This and this. These are the surviving terms. So now what do we get? If and only if, well, let's just go ahead and write it down. We've got 3/2 limit as n passes to infinity. So what survives? 1 and minus 1 over 2n plus 1. And of course, now the limit here is 1. And of course, as n passes to infinity, we just think about our calculus, that's going to be 0. So we get 3/2 times 1 minus 0, which is 3/2. So when we think about this particular problem and we consider what it is we had to do, the key is looking at the particular structure of the generating sequence. And when you start this problem, the idea, if it says compute the sum and you're like, I don't know much about infinite series right now. If they're asking me to compute the sum, it must be something that will simplify greatly when I look at the partial sum. And so what we're seeing is that in this particular case, the partial sum is very, very simple. The partial sum turns out to be very, very, very simple. And so we can easily pass to the limit. So now later on, you might look at this particular series and multiply it out and say, well, I'm going to apply this convergence theorem and it converges, and then you may just miss the fact that you can actually compute the exact sum. So the telescoping sums make a good example of how you can actually evaluate an infinite series by noticing the fact that the generating sequence produces a partial sum that telescopes. Okay, so what we want to be able to do, and if you did your calculus 1, if you prove that a continuous function is Riemann integrable, you generate a telescoping sum. So this is actually something you should have discussed in calculus 1. If you didn't, that's okay. But the idea is that this type of structure is a recurrence in mathematics. And it's kind of like we're doing a problem when we get the Pythagorean theorem and we're like, thank goodness I see something that's going to simplify the calculation. So the telescoping sum, this gives you a nice little recipe. So if you see a problem that says compute the sum, you look for this. And again, decompose and then follow the construct of allowing n to pass to infinity. Just remember, when you look at what we're doing here, we start out by making sure that our notation makes sense. We're already using n, so we have to choose another letter. We just use k. I don't care which letter you use. You can use another letter, but k seems to be the easiest. Okay, now what's another example? For instance, if we had to do an example in of convergence, and let me give that to you. Here's one more example. And it looks like this. For instance, consider the geometric sequence. And I like to use the notation that Larson and Dr. Stewart use in their calculus books and in their pre-calculus books. So for instance, we can think of, let's just say we're going to say A is non-zero. Again, fixed. And R, we're going to take to be non-zero, fixed. Before I give a formal statement of it, let's just look at some of the algebra here. So say we have AR squared, AR cubed, and then AR n minus 1, etc. So we're thinking the first term is A, the second term is AR, the third term is AR squared, etc. Let me focus that a little bit. And when we look at this, we're thinking, well, this is pre-cal. So we're thinking, okay, so is this going to simplify like the telescoping? And if you think about what you did in pre-calculus, you know what the answer is. So now we can say, all right, well, define. And what we want to do is compute the sum. Well, we want to compute the sum, you know, when it makes sense to compute the sum. And we'll use one of our special limits. So define S of n to be k equals 1 to n of A R k minus 1. So when we look at this, ladies and gentlemen, we're thinking when k is 1, we get A times R to the 0, which is that. When k equals 2, we get A R to the 2 minus 1, which is this term, etc. And then, of course, when k is equal to n, we just get the general term here. So this would be at least a rendering of the partial sum, and you're thinking that's not very helpful. So what do we do? What's the geometric part of this that's going to get us to the finish line? So consider the following. So what we have in this case is we're going to say S of n minus R times S of n. That is, remember back in pre-cal, we think of A as the first term and R as the so-called common ratio. So one construct of algebra says consider S of n minus R times S of n in hopes of generating what we just talked about, a telescoping sum. So, okay, well, I think we can do this. Now notice we can factor the S of n. So this will just be a 1 minus R times S of n. That is, if we just factor the S of n, we left with a 1 and a minus R. And then now we can look at the series. So 1 minus R, k equals 1 to n, A R k minus 1. Now it's like we're in pre-calculus again. And so now we're thinking, well, this is just a finite sum. Let's go ahead and multiply it out and see what we get. So we get, well, 1 times anything is just the anything. So we get k equals 1 to n of a r k minus 1. And now we want to multiply by r, just run it through. R is fixed, it's a constant. So we get minus k equals 1 to n a r. So now we have k minus 1 plus 1, which is just k. Now, of course, this is what you did back in Calculus 1, where what you wanted to do was make sure that you could add these, but you can't really add them when we don't have like powers of r. We know that doesn't make any sense. We know we've got an a in everything, and we could go ahead and factor the a, which we'll eventually do. So the thing is, it's like, how do we get these powers to be the same? Well, notice here, we need to make this bigger. We need to make this into a k and then compensate here. So if we re-index here, replace k with k plus 1, we need to re-index here to start with 0 because we make this one bigger, we make this one smaller. So let's re-index. So we have k equals 0. Now we go to n minus 1 since we adjusted by 1, a r to the k. So now when k is 1, notice we just get a. When k is 0, we just get a. And when k is n, we get a r n minus 1. And when k is n minus 1, we get the same. So these are equivalent. So then minus, I mean, this is simple, but useful, right? So now when we look at these two, notice we have a k equals 0 term here and a k equal n term, but all the other terms coincide between the two. So let's extract those. So now we've got the k equals 0 term. So I'm just going to say k equals 0. So this will just be AR 0 or just A. Then we have plus k equals 1 to n minus 1 of ARK. Now we'll do the same here. We want to extract the n term. So we have minus k equals 1 to n minus 1 ARK. And then, of course, when k is equal to n, we get minus AR to the n. Okay? So now we're thinking, here we go again, telescoping. Telescoping. The idea is that the majority of the terms just absorb, so to speak, and we're left with what? A minus ARN. A minus ARN. So like I was saying before, when I gave you the example of the telescoping, that was just to set up the example for the geometric, which again is telescoping. So they're not really different. You know, lots of times, oh, here's the telescoping and here's the geometric, which is really different. Well, it's different in a lot of ways as far as its characteristics, but it's still an example of a telescoping situation. And so now we see we're good to go. Notice here, equivalently, well, let's write what this is. I told you I was going to factor the a. So this is 1 minus r to the n. Again, very simple. And so s of n times 1 minus r equals a times 1 minus r to the n. What's nice about this is that it's very straightforward algebra and a little bit simpler than maybe what we've been doing. I don't know, just maybe not as hectic, but very straightforward. And so now if and only if S of n equals a times 1 minus r to the n divided by 1 minus r. So when we think about the last problem, I keep going back to this. Let's see. Where did I put it? When we analyze the S of n, it was very easy to pass to the limit, right? So now we analyzed the S sub n, just kind of looked at the partial sum by itself, just like we looked at the partial sum, did the partial fraction decomposition, okay? And then I could have done a little bit more work on that before I moved it to the actual infinite series, but your choice, my choice, whatever. Here, what I chose to do was go ahead and complete the algebra. Now we can move to the infinite series because this was a little bit more complicated. So now let's finish this off. So we'll take our calculation here and say this implies now that the infinite series, so we'll say n equals 1 to infinity a r n minus 1. Now we don't have to worry about any k's because the n has been replaced with infinity. This will be the limit as n approaches infinity of the corresponding partial sum, which is a times 1 minus r to the n over 1 minus r. So now, of course, we can factor all of the stuff that is constant, the a and the 1 minus r. Clearly, r can't be 1. We'd see that now. So we have the limit as n passes to infinity of 1 minus r to the n. Now we're back to our special limit. Notice in our analysis here that r is never equal to plus or minus, or say r is not equal 1. But I think you see that. Now you look at this portion of the limit. This will diverge to infinity when r in absolute value is greater than or equal to 1. But we can say equals a, we've done this calculation before with the p integral. This will be 1 minus 0 equals a divided by 1 minus r, if and only if what? Special limit, r in absolute value is less than 1. So when we look at this particular problem, we can sum, and this is a luxury.